I'm now going to talk a bit about internal domain-specific languages and a bit about state machines. It's going to be fairly quick, just to remind you what each of the different parts of the material is about. So, state machines, we have a bunch of state machines that we work with sometimes to use as an example. Microwave oven, the cooking hood, the CD player. And in all cases, we have states and transitions between them and conditions and actions. And that's what we need to think about how to represent. And our goal is to get to a compact and readable representation. And to that end, we need the right kind of internal representation. We need the right kind of model to represent the information that we need about the state machine. Now, here is sort of the model that we started with to begin with. So this is the standard object on the model. We have a state machine that is composed of a number of states. And then we subclass the state class. The state class is abstract, so we subclass it. So for example, this is for the microwave oven. We make an inactive, a door open, and a cooking state. And we implement the process event method each time. So this is the typical framework approach. It is less useful for a model for our domain-specific language because it requires introducing new classes. And when we want to do these models, we would like to have classes that describe the entire space of information that we need to represent, and then make object instances, model instances that describe the concrete program we want to have, the concrete model. So rather than this classical representation, we pick a representation. Oh, that's not, sorry. I was expecting a different one. So why did I have this one here? It looks like the same. Just a second. A slight confusion. Okay. So this is, yeah. So that's the, um, here, sorry. Here we have states that are subclassed and that each implement the process event method. So all the logic of how to process state changes is in fact hidden inside the process event method. We have a bunch of ifs, or maybe we use a switch, or we could write a loop or whatever down in the process event, which is in fact the logic, the key logic of how our state machine works. Now, here we have a different approach. Um, States have a process event method which says that we have a bunch of possible transitions. When we get an event, we look through and find applicable transitions. If we find one that is applicable, then we execute its effect and set the state to the target. So now the logic of how to change states is fixed. In fact, the way if you want, our state machine interpreter works is defined once and for all, which is good because then that reduces the risk of getting bugs. Now, the way we represent transitions now is that we say um, we have an object for each transition now, where before we had an object for each state. So now we have transition objects. Um, so now on each transition, we can ask, is this transition applicable? And we can execute its effect. And then we make subclasses for each of the specific transitions. Now we have more of the structure of our problem fleshed out into objects, but we're still making subclasses down here. Like a specific transition, well, we make a subclass to define whether it's applicable and what the effect is. Now, if we limit ourselves more not to arbitrary is applicable and arbitrary effects, but some specific ones, what we can do instead is to say that transition classes, for example, well, basically they're always comparing a variable to some internal state. So now we say, oh, the name of the variable is here. So if we go all the way back to the start here, it could be that for the cooking hood, we're saying when the power is equal to 1, and we get the minus button, we go from the on state to the off state. So that's the condition here, power equal to 1. And so basically all the aspects of what we want to write as a condition has been expressed as a single as fields of the class here, and now we can make transition instances. Like we say, we compare the track value, we test whether the or the track variable, whether it's equal to the value 0. Nay, no, sorry. So the problem here is, of course, now we're getting into this is very um, this is symptomatic. I'm having a hard time recalling what is the comparator and what is the argument. In any case, now we have the situation here where we can say it's checking whether the track is equal to 0. Oh, that's for the, of course, this is because we are we also probably also expressing the how to increment. Let's go back and look here. The CD player. Let's zoom in. I'm honestly, I find my code a little bit strange, but I think we have this transition here on the play event. If the track value is equal to 0, set the track equal to 1. Now there's something slightly fishy, but we're going to just ignore that now. So here, if track is equal to 0, then we set the value to 1 of track. So I really would expect that we would have two different variables, one to compare with and one to set, but and maybe we would want that to have then the full version. Okay, so now we have the capability of expressing the entire semantics of a transition, what to compare to, what is the effect, as an object. But working with this object is very hard. It's hard to remember what is the argument, what is the variable, what is this actually doing. So, and we can also look at, and now for a moment ignore the last line here. Because here we're looking at the code, so or rather we have different versions of the code. Here we're creating the on state, and with the version where you make define is applicable and effect methods, then when we add the transition, then we create a new transition subclass and another subclass and define the is applicable and effect methods with whatever we want to write inside them. With the last approach here, the transition object, we create it like this. So we just create a new transition object, track true equals 0, true, false 1, which is the one I have here. So rather than making subclasses, we now just make objects. We build everything from objects, which is the ideal setting for defining our internal DSL, which is the last thing we have here. So it's very easy to build our internal DSL front end that from this sequence of operations, state, on, to, set, and so on, this chaining of method calls, builds the same object structure. And now we use the names of methods to make it easy to see what's going on, rather than having an incredibly long argument list like we had here, where it's hard to see which is which. Then we have state on the plus event increment power by 1, but only when power is less than 6. That is fairly readable. Also after a long time and breaking your jaw and whatever. Whereas this here was more complicated. So that's it for the small state machine internal DSL thing.